Hello. In this video we are going to analyze the temporal response of the LJ Technical Systems servo system. Firstly, we will obtain a behavior model based on the study of the open-loop temporal response. We will then close a proportional control loop in speed and position output, and analyze the effect of the controller gain on the accuracy and stability of the closed-loop system. The LJ Technical Systems module corresponds to a DC motor and its power and signal conditioning stages. The module contains the necessary sensing elements to close speed control loops, thanks to the tachometer dynamo, and the position, thanks to the potentiometer signal. In addition to this motor is equipped with a magnetic brake. The steps to follow are those. First, we will analyze the response of the motor in open loop, taking as output the signal of the tachymeter dynamo and with which we will obtain the mathematical model. Next, we will close the loop with a proportional controller and analyze the responses for different values of Kp. Finally, the performance of the plant will be analyzed, sampling it with different sampling periods. The same steps will be followed by taking the potentiometer signal as output. As told before, the speed control experiments will be followed by taking the tachymeter's signal. This pin is on the right side of the plant, as it can be seen on the figure. In this figure, we can see the block diagram for the open loop experiment built in Simulink editor. Depending on the output we take, we will obtain different mathematical models, but the form of the response will be the same. What I mean by this, the output of the motor can be the terminal voltage of the tachometer dynamo, the motor speed in radians per seconds, relating it with the tachometer constant, or even the speed in revolutions per minute, relating the voltage with the speed by the help of the display that the engine offers. In this case, the response of the motor will be analyzed, taking the terminal voltage as output. In this video we can analyze how the motor is able to turn in both directions depending on the input voltage. We can also make it stop when no input is applied. But, what happens when the engine is moving and we apply or remove the brake? We can see that the velocity of the motor is reduced when applying it, and vice versa, when we remove the brake, the output increases. As we can see, the output resembles the response of a first-order system, so, in order to obtain its transfer function, the following mathematical formulas must be applied. As we can see, the model consists of two parameters, the time constant and the static gain. These parameters are obtained in the following way: the time constant is the time for the system step response to reach the 63% of its final value, and the static gain is the ratio of the output and the input under steady-state condition. In this way, for this system, the following transfer function is obtained. If we compare the output obtained experimentally with the ideal output, we can see they are similar. On the other hand, as we have seen on the video, in the case of open loop, this gain varies depending on the brake. As you can see in the image, if we apply the brake, the gain will be reduced considerably. Once the engine transfer function has been obtained, the tachymeter signal has been fed back and a proportional controller has been created. For this experiment, the following Simulink model has been done. In the following video we can analyze the behavior of the engine. In this video, the Simulink model shown before has been implemented with three different gains, Kp equal to 1, 2, and 5. As we can see, the higher the gain, the faster the response and the smaller the static error are. In this plot, it can easier be seen the concepts explained before. Finally, the accuracy and stability of the system have been evaluated with different sampling periods. As can be seen in the image, the loop is digitized with sampling periods of Ts, but the graphing is carried out at the maximum possible speed, at 5 milliseconds. The sampling periods of the plant are dependent on the graphing period, since they will be larger and multiples to it. To analyze from which TS we will have oscillations, we must obtain the digital transfer function of the closed-loop system. For this, first, the open-loop digital transfer function will be calculated using a zero-order holder. Once obtained the expression of the pole, we will equal it to 0, since the system will start to oscillate at that exact point. In this case, evaluating the equation with our parameters, we obtain that the system will begin to oscillate at 0.2 seconds of sampling time. In this case, theoretically there should be oscillations from sampling periods of 0.2 seconds, and as it can be seen in the image, the response of the system with this sampling period, the response of magenta color, has an overshoot, and with greater sampling times, the output is even more oscillating. In this case, for the position control experiments we need the potentiometer's signal. This pin is also on the right side of the plant, as it can be seen on the figure. As previously mentioned, the same experiments have been carried out for the position case. To do this, we have obtained a new mathematical model that represents the open-loop dynamics of position. This has been achieved from the mathematical model obtained in the previous experiment, where a reducer, an integrator, and the potentiometer constant have been added, in order to be able to relate the output voltage with the input voltage. In this video we can analyze how the response of the potentiometer is a periodical signal with saw waveform. Depending on the turning direction, the saw waveform varies, being symmetrical on the turning direction. As previously mentioned, the response of the plant in open loop is a periodic signal with saw waveform, since the plant is type 1. With which, to step type inputs we will obtain a ramp type signal. On the other hand, the periodicity occurs for each spin of the potentiometer axis. As has been done in the case of the speed control, a proportional controller has been designed. The Simulink model for the closed loop system is the one shown. In this video, the Simulink model shown before has been implemented with 3 different gains, Kp equal to 1, 2, and 3. As we can see, in all cases the stationary error is null, what change are the overshoot and the settling time. In this case, since the motor is of type 1, the stationary error will be 0, but the overshoot and settling time will vary depending on the gain of the controller. The higher the Kp, the greater the overshoot and the longer the settling time are, as it can be seen on the figure. Finally, the accuracy and stability of the system have been analyzed for different sampling periods. In this case, the graphing will be carried out at 5 milliseconds and the sampling periods of the plant will be bigger and multiple to it. For this experiment the following Simulink model has been implemented. In this case also, to analyze from what value the system will become unstable, as we have done previously, the plant has been digitized with the help of a zero-order holder and the closed-loop digital model has been obtained. In this case, we will evaluate the stability by applying Jury's stability criterion to the denominator. From Jury's criterion, we obtain that the range of the sampling period for the system to be stable is from 0 to 0.3 seconds. From this point on, the system will become unstable. As can be seen, at sampling periods of 0.3 seconds the system becomes unstable, which is the value obtained by doing the theoretical calculations.